Hey folks, in this video I want to show you a technique called reflection, where we take a propositional way of saying something and a computational way of saying something and show their equivalent. We've already seen some reflection in sort of the EQB lemmas, like EQB base if and only if, where we saw that, look, the equality function we wrote on bases is really exactly the same thing as equality on bases, like the equal sign. We're going to see it now for something maybe a little more interesting. We're going to use it to relate two notions of evenness. In the video after this, I'll sort of dig into a little deeper some of the distinctions between working in a computational world and in a propositional world. But for now, I just want to show you how the reflection mechanism works. So far now we've seen a couple different ways of talking about evenness. So one is we could say, well, the even b function returns true, right? That's a way to talk about which numbers are even. But then another, maybe the school definition of evenness is saying, look, a number is even if there's some k such that n is 2 times k, right? N is equal to double k. So I've written double rather than mult because it's a little easier to prove things about. Though we've already, I think, been able to prove that double k is equal to 2 times k, so just as well. Okay, so whenever anyone involved in any formal mathematics or logic sees two definitions that are really different but are meant to communicate the same thing, the natural thing they want to do is be like, well, let's prove that they're the same, right? Let's make sure that our notions of evenness coincide. If they do coincide, then the notion of evenness is strengthened, right? You found two different ways to say the same thing. That means it's maybe a thing worth saying. Uh, Also, if they don't coincide, okay, now you know something's really messed up or extremely interesting. So great, it's a super valuable activity to do. So let's do it. Let's see what it takes to get to do that. So there's like a variety of helper lemmas, some of which are optional, some of which are not, that lead up to doing the proof. I'm just going to sort of like walk through each of them. The general gist is, so even b and double are like annoying functions because they don't work in a single step. So we need to prove some lemmas that sort of let us characterize what a single step does. So here, for example, even bs works by sort of says like, well, this is another equation you could give for testing evenness, right? S of n is even if and only if n is not even. It's true. It's an interesting way to phrase it. Here's a straightforward theorem that the results of double are even. Right. This is thoughtless, really, at this point. Hopefully, it doesn't require much effort. You might even be able to look at this proof script and be like, "Yep, checks out. Great." And then there's this very clever theorem. Coming up with this theorem is actually quite hard. But the general idea says, okay, look, n, for every natural number n, there exists a case such that n is equal to, well, if it's even, it's equal to exactly double k. Otherwise, it's equal to the successor of double k. This is like a one-line definition of half on some level. Right, sort of like we're like knowing a little bit more about numbers than we normally get to put in play when we're just writing computations, saying like, look, n is going to be equal to one of these two numbers, and it just depends whether or not it's even. Okay, sorry if this gives you any midterm flashbacks. Okay, so once you know this theorem, proving it, I think, is not so bad. And once you have that, then we can prove this theorem. So this, to me, is, I think, the most interesting if and only if we've seen yet. It's saying, look, n is even, according to the function we wrote, if and only if there exists some k where n is equal to double k. Let's walk through the proof here. Okay, let n be given. This is an if and only if, so we've got to go the two different ways. So break it up. Okay. So now we need to show that if even bn is equal to true, then there's some k such that n is equal to double k. Okay, well, suppose n really is even according to our function. Okay, now we have a sort of a powerful tactic here. So what's going on here? It's a destruct of a compound expression. The compound expression is the application of a lemma. Right, now let's look. Even b con double conven. What type does that have? Gotta type it correctly. Even b double conven is a proof that there exists a k such that n is equal to if blah 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 blah. Okay, so it's an existential. So that means we could destruct this, saying, okay, give me the k and the fact that all this stuff. Right, we're really synthesizing all the techniques we've seen. Okay, let's do it. Break it up. Okay. So now we say hk is equal to this. A couple different ways we could go. The proof we have written here says, well, rewrite by hk, which is maybe not the direction you would think about, right? This is making it look worse. But then we rewrite by h, and now it's gotten much simpler. And now when you look at this, you say, okay, there exists some k0. Okay, nice name, cock, whatever, dude. Double k equals double k0. Okay, I got a k0, right? Just like pick the one that makes it easy. Now, maybe you'd like to go a different way. It might be easier to say something like this, right? Sort of like simplify hk, and then at this point, maybe you would want to say something like, I don't know, exists k, apply hk. That's a great proof too. You know, it's not particularly important. One other comment here. So like here, we're doing a compound destruct on this. If you didn't feel comfortable doing that or didn't occur to you to do that, you could say, okay, the assert there exists k, n equals if, even b, n, then double k, else s double k. So we're just restating hk or something. Oh. Then we could say apply even b double conv. Right, and now we could say, okay, destruct hk as k hk. Right, now we're back where we were. So you don't need to do this fancy trick, right? That's totally fine. Though I think it certainly is simpler than all of that business. Okay. Great. Okay, so this is, I think, the interesting direction of the proof, right? Where we're using this sort of clever lemma that's sort of like doing the half for us to do the proof. The other direction is, I think, pretty straightforward. So, okay, we know that if there is some k such that n is equal to double k, then even be untrue. Okay, break up the existential. Fine, give us the k such that n is equal to double k. Great, that means I can turn that n into double k, and I believe we're basically there, right? Even b double says exactly what. Okay, so this theorem says that even b reflects the logical proposition exists k, n equals double k. In the next video, I'm going to talk a little bit more about like why is that useful, why is that interesting, what's happening here, why is reflection a thing you might care about. Hopefully all this made sense. You'll have this proof script yourself. So if my run through of this wasn't super clear, I think it's worth like going through step by step and like trying to find the parts where you're not sure why it did what it did, and then maybe hit me up on Zulip. All right, talk to y'all soon.